Hey guys, welcome to right triangle trig ratio. So today we are going to be talking about everything in terms of right triangles. We're going to be talking about sine, cosine, tangent, cosecant, secant, and cotangent. And we're also going to solve some right triangles. So in this video, what we're going to see is okay, what exactly do these trig ratios mean? When I take sine of theta, what is it exactly that I'm doing? Okay. We're going to see, well, how do we use these to our advantage? What do we need them for to solve right triangles? And what exactly does it mean to solve a right triangle? And then we'll do two examples. So let's get right into it. So what are these trig functions? So these are the 6 trig functions we have here. Notice here that the input here, so remember, these are all functions. So functions, there's an input and an output. So the input here is an angle. So sine, you input into sine an angle. Same thing for cosine. You input here an angle. Same thing for tangent. Same thing for cosecant. Same thing for secant. Same thing for cotangent. The input is an angle. This is really important when we go to inverse functions. Okay, but the sine function, these trig functions, we're going to input angles and we're going to output ratios. So what are these? So sine of theta, and what the theta is you'll always mostly see a theta by convention. Theta just means angle of focus, okay? It just means the angle that we're currently talking about. Right now, theta means, hey, this angle over here. But theta can change, okay? Theta could have been this angle. Rarely ever is it the 90-degree angle because we know what sine, cosine, tangent, and everything is of 90 degrees. So rarely do we consider the 90-degree angle. We mostly consider the other two angles, okay? So now, what about all of these ratios? What does it mean? Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and so on. What do these guys mean? Well, if I input an angle into sine, what it's going to give me is it's going to give me the ratio of the side opposite of that angle divided by the side that is the hypotenuse. Now the hypotenuse is always going to be the longest side of the right triangle, or also better known as the leg that's directly opposite from the right angle. So the hypotenuse will always be directly opposite of the right angle. Opposite, so remember theta is all, theta could change. Right now theta's here. Opposite means the angle literally furthest away. Opposite, right? I had to kind of take a hike to get over there. Now what about adjacent? Adjacent angles, because we almost never reference the right angle, I can say this. Adjacent angles are always touching, right? This angle here is touching theta. This is actually connected to theta, and it's not the hypotenuse, right? For either of these two angles, they're either touching the adjacent angle or they're touching the hypotenuse, and the hypotenuse is always set at the longest side. The opposite side could change, and the adjacent side could change depending on what angle we are referencing. Right now, in this particular diagram, with this being theta, that's the opposite side, and that's the adjacent side. But things can quickly change if I said, okay, well now I'm saying theta is over here, which would make this side now the opposite side, and this side then would become the adjacent side. So adjacent and opposite can change depending on what theta you're looking at, depending on your angle that you're referencing. If I'm referencing this angle, then that's the adjacent side and that would be the opposite side. If I'm referencing this angle, then that's the opposite side and that's the adjacent side. Just always remember, adjacent means touching, and it's not the hypotenuse. The hypotenuse is set no matter what angle you're looking at. Okay. So let me erase this, and let's get a little bit more into it. So let me give some examples. So again, we input angles and we output ratios of sides. This is all very, very unique to right triangles. If we don't have a right triangle, all of this goes up in smoke. None of this means anything. So theta, suppose theta was 30 degrees, and this was side length 1, and this had side length 2, and this had side length square root of 3. Okay? So sine of theta, the way that I would write this, okay, well sine of theta, well theta is now 30 degrees, so we would say sine of 30 degrees, remember sine's a function, I'm inputting an angle. This is equal to the opposite side, which is 1, divided by the hypotenuse, which is length 2. So if you put sine of 30 into your calculator, you will get 1/2 or 0.5. Now if you put cosine of theta, and remember now we've said, okay, theta is 30 degrees, cosine of 30 degrees is equal to the adjacent side over the hypotenuse side. The adjacent side in this case is root 3 over the hypotenuse, which is 2. So the cosine of 30 degrees is square root of 3 divided by 2. If you put this in your calculator and you get the decimal, you put that in your calculator, you get a decimal. You put that in the calculator, you will get the same decimal. Okay. Now for tangent, we have opposite over adjacent. So now if we took the tangent of 30 degrees, so the tangent of 30 degrees is the opposite side, which is 1, divided by its adjacent side, which is square root 3. So the tangent of 30 degrees is 1 divided by square root 3, and if you rationalize the denominator, this would be root 3 over 3. Now we're not going to get too much into cosecant, secant, and cotangent because a better way to remember cosecant is the reciprocal identity of sine, right? If sine is opposite over hypotenuse and cosecant is hypotenuse over opposite, these guys are reciprocals. So sometimes a better way to remember this is just simply 1 over whatever sine theta is. So whatever we got here. So if sine of theta is 30, if sine of 30 is 1/2, then cosecant of theta or cosecant of 30 would be equal to 2, right? 2 over 1. In other words, we flipped it. Secant is just the reciprocal of cosine. So whatever we get for cosine, if we're trying to find the secant, we simply flip it over. So cosine of 30 gave us root 3 over 2. So secant of 30 would give us 2 over root 3. And cotangent, as you can guess, is the opposite or reciprocal of tangent. So this is 1 over tangent of theta. So if tangent of 30 degrees was 1 over root 3, and cotangent is its reciprocal, then cotangent of 30 degrees would be root 3 over 1, or better just known as root 3. Okay, so let's see these guys in practice. So in the two examples I'm going to use, we're going to solve right triangles, and we're going to see how these are useful to figure out every angle in a right triangle as well as every side length. So what does it mean to solve the right triangle? Solve the right triangle means find me every angle in a right triangle and tell me what all 3 sides are. So tell me every angle and tell me every side. I'm going to write SOHCAHTOA over here, which is a mnemonic that you'll hear a lot of people use. I don't use it myself, but because it's so widely used, I put it in my videos so that you can reference it when other people say it. So this is to remember that sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. I, however, personally don't remember it that way. I was brought up in school system a little bit while ago where saying things like these were still acceptable in classrooms. But I remember it as old hippies are high on acid. And to this day, that is how I remember it, and I will always remember it that way. And I don't use SOHCAHTOA, I use old hippies are high on acid, and this will work for me for my entire math career, and I still use it. But it's not exactly the most politically correct thing to say. So, anyway, let's solve this right triangle. So, I know that this is 90, I know that this is 36, so how could I figure out this angle here? Well, all the angles in the triangle have to add to 180, so if I subtract 90 and then subtract 36, I will get 54, which means that angle is 54. So all of my angles are solved for. Now I just need to solve for my sides. So I can either use 54 or I can use 36. It really is, it's all going to work out the same. I'm just going to use 36 here as my reference angle. What do we know? We know our hypotenuse, right, because side opposite of the right angle. We know our hypotenuse is equal to 10. So we know hypotenuse is equal to 10. If I'm referencing the angle of 36, then that's the opposite angle. So this then would be So A would be opposite, and the touching angle, or B, would be my adjacent angle. So I don't know what my opposite angle is, or sorry, angle. I don't know what my opposite side is, and I don't know what my adjacent side is, but I can figure those out using trig. So if let's say I want to find A. So A is the opposite side. Which one of my trig functions deal with an opposite side and a hypotenuse? Let's see. Well, it's sine. Sine is opposite over hypotenuse, which means sine of 36 input angle equals the opposite side, which is A, over the hypotenuse side, which is 10. Now we have an equation set up of one variable. We can solve this. We multiply both sides by 10. So 10, 10 to get the 10 out over here. So we'll get A on the right. A is going to be equal to whatever 10 times sine of 36 is. So let's see, A is, 10 times sine of 36. Well, 5.9, we'll round. So this is equal to 5.9. Okay, so we figured out A. A is equal to 5.9. So now we just have one more side to solve for B. And we can do this a bunch of different ways. But I'm going to use the tangent. So tangent is equal to opposite over adjacent. So tan of 36 is equal to the opposite side, which is 5.9, over the adjacent side, which I don't know. Okay, well, how do I get B out of the denominator? Well, I'm going to multiply both sides by B. Okay, when I do that, I'll have B times tan of 36 on the left, and I'll have 5.9 on the right. How do I get rid of tangent of 36? Well, I'm going to divide out by it on both sides. Tangent of 36. Tangent of 36. I go between capitals and lowercase, and I really shouldn't. But excuse my math faux pas. So what is 5.9 divided by tan of 36? Well, let's see. 5.9 divided by tan 36. We get approximately 8.1. So B is approximately 8.1. So now our triangle is solved. We know every angle in the triangle and every side. And we are done. Let's go to our next one. Alright, solve this right triangle, and we're going to do this quickly. So this angle here, 180 minus 90 minus 62, 180 minus 90 minus 62, to find the remaining angle. So this will be 28, so all angles are solved. I'm going to write our little SOHCAHTOA here as a reference again. SOHCAHTOA. Okay, I need this side and I need this side. Well, this side here, because this is a cross, this is going to be my opposite side. This side here, because we're touching, this is the adjacent side here. I know, or I'm sorry, even I got screwed up. That's the hypotenuse. This is the adjacent side here. This is the hypotenuse because it's across from the right angle. So, quick trig. Alright, opposite over adjacent. Okay, opposite over adjacent is tangent. So, tangent of 28 is equal to opposite, which is, I don't know, we'll call this A, we'll call this C, is equal to opposite over adjacent, which is 25. So I'm going to multiply both sides here by 25. 25. So A will be equal to 25 times tangent of 28. And that's going to be 13.3. So little a, so this side is 13.3. Alright, one last thing to solve. I need to solve for the hypotenuse. I could also use a squared plus b squared is equal to c squared. That's an option as well, but let's practice the trig. So we'll use 28 again, opposite over hypotenuse. Sine of 28 equals opposite over hypotenuse, which is c. Multiply both sides by c. Oops, 13.3. C times sine of 28. Divide both sides by sine of 28. C is going to equal 13.3 over sine of 28. So C is going to equal sine 28